Well, I can tell you that if you liked it so far, it's going to get more and more interesting. Okay, it's really quite magical what comes out of group theory in the end. For that, we have to understand this idea of conjugacy classes very well, and then from next time we will start representations, and that is where all the power of it comes, because in fact chemists, they use group theory all the time, but if you use chemistry books or chemistry lectures, presentations, they never teach any of this background. They have shortcut rules for figuring out the character classes of molecules, and they just fill out tables and then they quickly can see selection rules or multiplicities of degeneracies of state, transitions and so on. But we being physicists, we will labor through all the reasoning why those things work. So, but of course not labor as much as mathematicians. So let us just try to gather all the things that we have been studying. So the early parts were of course group, subgroup and coset spaces. And Lagrange's theorem. Has to be an integer. So now we are on to the idea of conjugacy classes and also the representation in cycle notation. So currently what we are going through is conjugacy classes. And of course we are adopting cycle notation alongside. So today we will see some comprehensive picture of all of group theory in some sense, okay, emerging from these things. But just to complete these ideas, the thing to remember is the overarching theorem, Cayley's theorem, that Sn is sufficient to embed any group we know, okay. So sufficient to include any group of order n as a subgroup. And this is of course Cayley's theorem. And the proof, these are called constructive proof, where the proof is not just a clever argument, but it actually demonstrates by in detail why the thing works, which is the, I don't know whether it is called in literature like this, but let us call it Cayley map. The map is that for corresponding to any pi of any g, element g of group G, there is a permutation G which can be written out as 1 to n, and then the fate of G of 1 G of n. Okay. What is the effect of the group operation G on 1, group operation or G on n? We will be shifting these definitions for convenience, but they will be defined clearly in the context in which they are being used. So we have this map, and we saw that this leads to some interesting results. Two of the important results. One is that the groups G through this embedding are realized as groups consisting of regular cycles. Okay. So there is notion of regular cycle, which contain identity or only those elements of Sn which necessarily change everything, shift all the elements, permute all the elements. And let me remind you here a little bit, permute all the n objects in the carrier space of Sn. Okay. So, the regular cycles are those that will necessarily change everything. What is carrier space of Sn? It is any set that contains some n objects, and it is called carrier space because by operations on this space we can realize the elements of the group Sn. So these two, so we have to add identity as a special case because somebody legally will say identity doesn't touch anything else, anything at all. So yes, so that is the only one that is an exception, but everything else is necessarily something that shifts everything. Now one can check that, and this is where there was some ambiguity last time. Partly it arises because this book Hammermash, which contains everything, but it is scattered and not punctuated very well. You know, the concept where the definitions begin and where theorems begin and end, these things are not punctuated very well. It's like a big rush of ideas. So I got a little confused there. But if I disentangle what Hammermash book says, then basically you can, we could have directly stated the following theorem, that all embeddings of G with G equal to n into Sn are as regular cycles. Need not call a theorem, this is actually more like a proposition. It's a fact which is sort of obvious from construction. So this fact follows simply from the fact that the group multiplication is unique, so that the multiplication table always has all the elements being permuted, the n elements, and therefore when you embed them in the big permutation group, they necessarily contain cycles of this form. Okay, that is the statement. So they are all necessarily regular cycles or identity. So this is one general result. The second result is that when you consider this embedding, the elements represented in this way are necessarily ones with equal number of elements, cycles of equal lengths. So proposition 2, so call this proposition 1. Is that of a group G get embedded as cycles, as elements of Sn made up of cycles of equal length. And this fact follows from the construction from proposition 1 that such embedding has to be necessarily regular. So I will just say check rather than proof. The check is that you will have some number of cycles representing g, pi of g, let's say, and let us say this cycle has length L1 and this cycle has length L2 and so on. Then we can see that pi g to power L1 will result in exact same order as original in this slot, the first slot, in first cycle. Can you see it? Yeah. Whereas here we don't know what happens. If L2 and L1 are not compatible, if L2 is a factor, if L2 is a much smaller number and a factor, then it may be okay. But if L2 is comparable and larger and not having a integer fraction with L1, then this L1 cycling will leave L2 in some unusual configuration which is not same as original. But we already concluded that if one piece is same, then all others have to be same, because otherwise you will have two different group elements having same first cycle, which is also not possible, because it means that in their multiplication table the first L1 entries are same. This cannot happen for two different group elements. Okay. So this means that it cannot be, so this means cannot be consistent embedding unless L2 equal to L1, etc., due to the properties of multiplication table. Okay. So that this consistency requirement comes from the property of the multiplication table from which you constructed this embedding. So these two facts are interesting facts for embedding of n into Sn. Now let us go over some caution about the cycle notation and how to manipulate cycles. So here what I have tried to identify is the fact that one thing is that if you have a permutation which is an n cycle, this n need not be size of the group, it could be any, I could have written R, okay. But if you have 1, 2, 3 R, an R cycle, if you want to write it up as a product of transpositions, then it turns out to be, the answer turns out to be 1n followed by 1n minus 1, so transposition of 1, 3 and transposition of 1 and 2. So you can check that, you can read this from right to left because we want this to operate on something, that it is this sequence of transpositions that makes up the cycle. In other words, there are n minus 1 transpositions in an n cycle. Okay. So whether a cycle is odd or even is decided by this list, and it contains n minus 1. The oddness or evenness has to do with whether n minus 1 is odd or even. Okay. So a 2 cycle, which is transposition itself, is necessarily odd, right, because it makes one change. So an even numbered 2, you remember it like this. If it is a transposition with only 2, it actually results in an odd cycle. If you have a usual cyclic permutation, as we say in physics, 1, 2, 3 go into 2, 3, 1, then that actually involves 2 permutations, and therefore 2 transpositions, and therefore it is even. So, and that is a odd there are odd number of entries in that. So there is n minus 1 is the number that decides whether this n cycle is odd or even. The other, this is an interesting trick that I read in Hammermesh. I don't know right now how to illustrate, or I have probably not given a problem based on that. But it is interesting to know this, that suppose I have one cycle which is A1 dot 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 A2, then some other element follows AR and goes up to AP. So this is a cycle in the sense that A1 goes to the next one up to A2, then A2 goes to R and then continues up to AP. Suppose you take this cycle but hit it on the left with an A1 A2 transposition. Okay, subsequent to doing this cycle, you do a A1 A2 transposition. What does this do? It actually breaks up this cycle, because this instruction says that A1 and A2 are now exchanged. Now here what was happening was that A2 was going into AR, but now that is no longer the case, because A2 is now supposed to go to A1. So that account kind of closes this cycle. So this becomes a cycle by itself, and AR has nothing originating it, so it begins a new cycle by itself. So there is this kind of a rule that operates for, if you manipulate in terms of cycles, then this is one way of that it will enter. And in reading all of these, I would say this general warning: carrier space versus operations. So the explicit notation with 2 rows that we have, actually each row denotes state of the carrier space. Displays states of the carrier space. Right, because it shows 1, 2, 3 going to A1, A2. So this is the initial configuration of the carrier space, and after the operation of this, it will become this. That's what it is showing. On the other hand, the cycle notation directly contains instructions for operations. For the group operation. So this is worth remembering if you ever get confused about what is happening, which at least I got for some time. So I have written here in the explicit notation of 2 rows, each rows denote the state of the cycle space. The n objects are listed out. It is meant to represent a group element, an operation, by displaying the carrier space in the 2 copies of the carrier space. On the other hand, the cycle notation is, especially the assertion I made, depends on, you can always break it up into these transpositions, and then that can be seen as a set of instructions for what to do on carrier space. Transpose this pair, etc. Okay. So that is what the difference between the two is. Anyway, so these are general comments for to keep in mind when you are trying to understand or calculate. Now we come to an interesting statement about conjugation, of this conjugation operation. we did one example and I tried to see if there is any other reasoning, but turns out there is the kind of problem that I gave, in which the A is, so look at this equation, B equal to sigma A sigma inverse. This is what we mean by a conjugacy transformation. The problem given there gives you B and A and asks you to guess sigma. And this kind of a problem doesn't seem to have any simple ways of doing, and at least the simpler problem that we gave, it was possible to make guesswork, but I couldn't see any generalization of that. But there it works, what the solution we got in class is correct, but I couldn't find any general way of checking. If I find, I will let you know. For the time being, I want to show you what happens when you carry out such a conjugacy operation. In the two row notation, there is some very interesting thing that happens. So consider a element A 1 to n, where the new order is A1 to An, and we call this A. And consider the transforming element sigma, which is 1 to n and then called S1 to Sn. But now we also play a trick, and this is the crucial trick. Note that we can always also write it by list some random elements A1 to An, and all we say is that the second row consists of whatever happens to A1 under operation sigma, under the fate of A1 under sigma. So this is saying nothing, it's a redundant statement actually. If you see that sigma, well, sigma, if you wrote it into, in fact you can consider it as a prescription for how to write the two row notation for sigma. The instruction is that given an element A1, in the lower row you must write the fate of that element under the operation sigma. That's all it says. Okay. But certainly, therefore, I can write out sigma in this form. This is the sub commentary Hammermesh does not give. So, okay. So the only clever thing we have done here is we have chosen this top row configuration to be whatever is going to appear in A in the bottom. Okay. Now, so this is how we write sigma. Now we proceed to compute this B, which is sigma A sigma inverse, in which we write A, of course, as defined here. We write sigma inverse by taking this thing upside down. Clearly sigma inverse is this thing upside down, right? It is the inverse operation of sigma. And the first factor sigma we write in this format. Okay. Now what is clever about this is that now we can start cancelling. We can cancel this 1 to n and get it to be S1, S2, Sn going to this, right? Or we can see it. S1 goes to 1 and after that 1 is going to A1, S2 go to 2 and 2 is going to A2. So after I complete this multiplication, I will basically have S1 to Sn in the first row and A1 to An in the second row. But now I can do the second operation where I cancel off the A1, A2, An row, so that I am left with an answer S1 to Sn, and correspondingly the lower row is sigma of A1, sigma of A2, sigma of An. So B is of this particular form. Now, as I said, the trick is in introducing the two equivalent ways of writing sigma, which were clever. The result is now very interesting. I should have highlighted this. So if somebody hands you A and then hands you a sigma, you can proceed to write out B without having to suffer all this by just putting the first row of B to be whatever is the second row of sigma. Okay. And by putting in the second row whatever is the effect of operation sigma on the second row of A. Another way of saying it is, once you understand what these instructions sigma are, 1 goes to S1, 2 goes to S2, you take these instructions, apply them to the top row by itself. That will produce this row, right, because it sends 1 to S1 to, and secondly apply the same rules to second row independently. So whatever sigma is supposed to do to A1, put it here, whatever sigma is supposed to do A2, put here. The set of instructions are all here. What happens to each A1 value is written here. In other words, the transformation amounts to applying the sigma operation separately on upper and lower rows of A. That's what it boils down to. And why does this work? Why does this magical looking thing working? To find the conjugacy transformation, all I do is apply conjugacy individually on the top row and bottom row. It is one of the comments I made earlier about the 2-row representation. What does 2-row representation have? Shows the state of the carrier space. And the conjugacy transformation is something that, so you remember the vector space example. On a vector space, remember linear algebra. Here, if I have, suppose I have OA equal to B. Okay, so where A and B are column vectors. I should have used a new page. So O is a matrix and A and B column vectors. Now you know that if you think of this in an abstract sense, the column vector is after all some components, and if it is supposed to be something physical, then it has some meaning of its own. The individual numbers don't mean anything, the whole collection. But this array has an independent meaning as an array only if the numbers are arbitrary, because they are only components with respect to some basis. Right, so you can change the basis. So consider basis change of basis transformation. A prime equal to S times A, where S is again n by n matrix. N by n matrix should be non-singular. And B prime should naturally be shifted to S times B. The components will change because you rotated your basis, or even you could even stretch and strain, doesn't matter. These are general linear transformations. Then that same operation OA equal to B is reproduced in the new basis, provided we should prescribe O prime equal to S O S inverse. Then I can make this whole equation OA equal to B read in the new language by applying S to the left. S on OA equal to B goes to S OA equal to SB, but SB is equal to B prime, and by inserting a SS inverse here, right, so we have to prescribe here SO S inverse, then I can put A prime here by putting a SS inverse there, right. So the kind of transformation we are talking about, conjugacy transformation, is well known in linear algebra as a similarity transformation. So when similarity transformation seems to act quadratically, sigma A, sigma inverse, on the operators, on the carrier space, there is only a linear transformation. And that is exactly what is happening in our 2-row notation, because the conjugacy transformation amounts to doing conjugacy transformation on S as a carrier space list, and on the second one also as carrier space list. That is what is happening, because these are carrier space, the vector space on which the groups act will eventually act as matrices. In fact, we will be using that as a representation. Okay. So I think once you understand, it is quite trivial, but it is interesting to note. This is about regular cycles. Yeah, this we went over first, theorems of equality of lengths of cycles for regular cycles which form order n subgroup of Sn.